Many people are unaware of the role environmental racism and injustice play in the world we live in. One might ask, how can the environment be unjust or racist? The terms, however, don't refer to the literal environment itself. The Environmental Injustice Organization's Liabilities and Trade Project defines environmental injustice as the fact that some communities or human groups are disproportionately subjected to higher levels of environmental risk than other segments of society.
Facilities such as landfills, toxic waste plants, oil refineries, and major highways are intentionally placed in minority dominant communities that historically do not have the advocacy and funding to refute these placements. The residents in these communities are already disadvantaged by many facets of America's structural racism, and they end up with chronic illness and disease without the income to move away, access to sufficient health care, and environmental racism continues to deepen roots of inequity and maintain their poverty cycle. An egregious example of environmental racism includes the 85-mile stretch of land along the Mississippi River between New Orleans and Baton Rouge, lined with oil refineries and petrochemical plants known as Cancer Alley. The residents of this area are 50 times more likely to develop cancer than the average American, and those who live here are predominantly black.
Similarly, in 2010, the Tennessee Valley Authority transported millions of cubic yards of coal ash from the spill into Uniontown, Alabama, a predominantly low-income black community. Other examples that may be more familiar are Flint, Michigan and its water crisis, or Los Angeles, California, where black, Latino, and low-income California residents are more likely to live near oil and gas wells that spew toxic pollution.
The EJ Index combines environmental and demographic information to reflect a census block's score for 11 respective environmental indicators. Each geographic location gets an EJ Index score for all 11 factors that is calculated by combining the environmental indicator measurement, the minority and low income percentages of the block group compared to the national average of approximately 35%, and the population count for the block group. The higher EJ Index score, the better, and the more negative the score, the worse or more disparity prone.
The three main datasets we used included the 2020 U.S. EJ Screen CSV, the 2014 National Emissions Inventory CSV, and the 2021 County Health Rankings National Data CSV. The API we utilized was the EPA's Air Quality System API called Air Now, and the HTML we scraped was the American Lung Association's Asthma Trends page.
The data cleaning process started with the EJ Screen dataset as we needed to decide the scope of our project. We sliced out columns irrelevant to us, such as the intermediate mathematical calculation columns, demographic info, and mapping info. We replaced empty columns with zeros as we weren't calculating averages with this set. We cut the length of measurements down to 4 digits and cast them as float type, and we changed the scope of our analysis to state and county, cutting a 12-digit ID code down to 5 digits. After we created a data frame with the info we wanted to look at, we calculated the minimums, maximums, and first and third quartiles of the EJ scores of each environmental factor so that we could locate the best and worst ranked counties for each of the 10 indicators. Note, we didn't use the PM 2.5 measurement, as that's what we used our API for in a later step. We used .indexmin and .indexmax on all of our maxes and mins to find which state and county FIPS codes correlated to each best and worst county for each indicator.
For our web scraping requirement, we used Beautiful Soup to scrape the race and ethnicity data from the American Lung Association's Trends in Current Asthma Rates table.
We used the Air Now API to acquire PM 2.5 measurements for the best and worst ranked county of each environmental indicator respectively. The PM 2.5 measurement is the measurement of particulate matter in the air in micrograms per cubic meter. We used the clean EJ screen data to locate the FIPS codes and sorted each environmental indicator column in descending order so that we could obtain the top 10 or so FIPS codes, as the Air Now API didn't have air quality data for every single county code, so we needed a list to iterate through in case the absolute maximum didn't have the corresponding PM 2.5 data on the API. We plugged our FIPS codes into the API and scraped the PM 2.5 sample measurement on the arbitrary date of June 16, 2020. It's important to note that our picking of an arbitrary day could be considered a weak basis for correlation later on in our insights.
And here we did the same thing, but for the worst scoring counties. It is essentially part 2 of what we did for the good scoring counties, as you can see here. We used the same arbitrary date of June 16, 2020 to obtain the PM 2.5 measurements from the API. Also, for these bad ratings, Most of the counties were ranked the worst in multiple categories, so there are only 4 different counties as opposed to 10 for the good. This makes sense as a county facing environmental pollution and inequity is likely going to suffer in more than one environmental indicator.
In our analysis, Cook County, Illinois scored both the best and the worst in diesel particulate matter in the air. How could this be? Well, when we cleaned the EJ dataset, we decided to keep the scope of our project to state and county. However, the actual EJ screen dataset breaks down geographic areas even farther than county. It makes sense that Cook County could have both the best and the worst scores because this county is home to Chicago, and within this county, there's a lot of disparity in terms of wealth. Wealth disparity is especially prevalent in cities and urban cores. America's zoning laws, systemic racism, lack of multimodal transportation, lack of mixed income housing, urban sprawl, white flight, and environmental injustice are all closely knit.
We found that the best scoring neighborhood for diesel particulate matter was River North, a wealthy, predominantly white neighborhood on the north side of downtown Chicago, with a median household income of $113,000 per year. The census tract that scored the worst was South Lawndale, colloquially known as La Vallita, a predominantly Hispanic neighborhood with a median household income of just over $33,000 a year, and only 45% of the population completing a high school education. This graph represents the particulate matter measurements of each of the best and worst ranked counties for each environmental indicator. We see here that the average particulate matter measurement is higher in the worst rated counties, with just 2 best counties ranking higher, and 2 counties having the same measurement.
Here we used the emission facility dataset and good and bad county info to create a data frame that includes the good counties and their respective count of emission spewing facilities, the bad counties and their respective count of emission spewing facilities, the average, minimum, and maximum number of emission spewing facilities in the bad scoring counties and good scoring counties respectively, and the average, minimum, and maximum number of emission spewing facilities across all the counties in the dataset. We used Import Wizard and SQL Workbench and PyMySQL to group by county, and as you can see, the average count of emission spewing facilities grouped by county is 178, which is significantly smaller than the average count of both the good and bad county groups respectively.
Here, we combined our good and bad county data with their respective emission facility counts that we just found, and used MySQL and SQL Workbench to calculate the average latitude and longitude for each county for our bubble map visualization.
We created 2 bubble maps. One here shows the count of emission spewing facilities of the 13 good and bad counties, and one shows the count of all emission spewing facilities by county in the National Emissions Inventory file. Next, we used our 2021 Health County dataset to look into the health outcomes by ethnicity of the counties we discovered to have good and bad rankings. We calculated the averages for both of the groups for the categories we saw relevant, such as lifespan, median household income, and population breakdowns. We see here that our bad counties actually rank higher in overall lifespan average and show a lower percentage of people with limited access to healthy foods. Again, this is due to the overgeneralization that the Environmental Justice Index spans across an entire county. It is unfair to assume, however, that these percentages are representative of the specific block codes that correspond to the actual extreme EJ index values. Aligning with our knowledge about environmental injustice, however, we did find that the bad-ranked counties ranked higher in the segregation index, traffic volume, and severe housing cost burden. We also found that the average percentage of white people in the good-ranked counties was approximately 63%, and the average percent of white people in the bad-ranked counties was 33%, aligning with our knowledge that minority communities are the most affected by the negative impacts of emission-spewing facilities and dangerous waste.
Interestingly enough, we see here that 80% of the good-ranked counties were reported to have water violations, and 75% of the bad counties did. It is unsupported to apply these findings to the entire population of bad-scoring versus good-scoring EJ index counties, as we were limited to counties that worked with our API, and we have a very small sample size. With the same caveats, we see that the bad counties rank in the first and second quartiles when ranked against all the other counties in their state for health outcomes, but we see that the good counties have some counties ranked in the third quartile. Again, this isn't consistent of our knowledge about environmental injustice due to the scope of our analysis and the sample size.
While the scope of our project limits us from making population claims about environmental injustice, the insights we concluded did reinforce what we know about environmental injustice, especially with the deep dive we did into the disparities into Cook County. Our insights and visualizations strengthened our claim that the consequences of hazardly environmental precipitates disproportionately affect poor people of color and reinforce the poverty cycle. Environmental injustice is a growing issue as sea levels rise and climate change worsens, and it is an extremely important, yet under the common radar inequity that policymakers and citizens must join forces to combat together.